Well, everybody who's watched King of the Hill knows that.
Huh? Oh, I guess so. I knew that before King of the Hill. Something really else fan.
All right. Talking about coils. Zach wrote a song about it. Want to hear it? Here it goes. All right. A, B, point C. C, how much counter EMF, or we could say now inductance. And remember, inductance is the fancy word for the opposition of current flow. How much CMF or inductance produced is determined by one, it's a little bit of repeat, core material. Right? We just talked about that. Core size. The number of turns. Or windings, that's how many times the coil went around. And the size of wire. All of that plays an effect on what's happening. And here is where I will do you a favor. My next point would be determined by the formula. L equals 0.4 times pi n to the second power UA, where n is the number of turns. So more turns equals more inductance. Maybe I could write that. Nah, it just gets... There's a lot that goes into that. So core size would be thickness, length. We don't have to get into that, so I'm just going to let you off the hook on that. All right? And I'm not going to do the big formula and explain the whole formula, the red line. So don't do that, Kevin. You just make people like freak out. So, all right. Inductance is measured in, do I hear volts?
Yes.
You'd be wrong. Henry's.
Oh, okay.
Of course. It's Henry's.
Definitely not Marvin's. I remember Henry.
You remember Henry? What's his first name?
Jeffrey? Hurt.
Named after Joseph. Henry.
Never trust a guy with two first names.
Henry.
Yeah.
He's partner, I don't know what kind of partner, to Michael Faraday. Who gets the honor of capacitance, the farad. I'll put that there. F-A-R-A-D. Farad. So that's Michael Faraday is the farad dude. All right. That was just your gee whiz information for the night too. That's a Phil thing. Yeah, I gotta find my own. So Henry is defined as, define it here, a conductor. Conductor has an inductance of 1 Henry if a current that changes at the rate of 1 amp per second produces 1 CMF of 1 volt. So, a conductor has an inductance of 1 Henry if a current that changes at a rate of 1 amp per second produces right, just in my notes. A CEMF of 1 volt. A Henry can be calculated where CEMF equals negative L delta I over delta T. Example, what is the CMF of 10 Henries when the current changes from 5 amps to 3 amps in 1 second?
Hold up.
I'm going to skip that part. How's that sound?
No.
I'm going to skip that part.
Okay.
You don't need to know it. Yeah.
So on C, you put how much CMF and you put inductance. That's CMF is voltage. So I'm not understanding how, if they're kind of the same, how inductance is a different symbol, vary in volts.
Okay.
So on the previous point.
Let me see if I get this. You're just kind of confused that EMF, CEMF, and inductance are all kind of the same thing, but you got to use them differently.
Yeah.
Okay. So let's dissect that a little bit. So and you can almost think of them as the same thing and not even get into trouble with it. It actually works that way. So let's see, a conductor has an inductance. Now an inductance is an equivalence of resistance. See, so it's not really CMF at this point. Think of it now as resistance, coil resistance, if you will. So inductance equals coil resistance. I like that. Of 1 Henry, if the current that changes the rate of 1 amp per second produces a counter EMF, a counter voltage of 1 volt. So you're okay if you don't fully grasp what I just wrote right there. Now I did because I want you to know that. I mean, that's what it is. So if somebody says, well, didn't he tell you what a Henry is? Of course he did. It's, this counter. So you're going to be fine if you can't see the nuances between those.
Okay.
What you have to understand, though, is that basic concept that as the current comes in, a coil resists it. As it wants to, as the current draws down, it wants to resist it. So it keeps it from building up, it keeps it from dropping down. It's always doing the wrong thing. What is this, number 11 now?
Yes.
Something like that.
No, it's an actual thing.
Yeah. On
11.
Yes,
We're getting to the good stuff here.
yeah, we're changing gears again.
No. No, this is a repeat of what I already said. All right. I'm like, do I really want to go over this? I do. Okay, inductance. Because I look at it, I go, well, I already said this, but I guess you didn't write it. Inductance in DC circuits. Again, we go back to DC because it's easier because crawl before you run, right? So in a DC circuit, the only changes in current, is when, what?
Turn it on.
Yeah,
Turn it on.
there you go. When the circuit is turned on or off. So in a DC circuit with only resistance, this happens at the speed of light simultaneously. It's not a problem. So in a DC circuit with only resistance, this happens instantaneously. This happens instantaneously. However, in a DC circuit with inductance, current no longer changes instantly. So now we're going to add, you're used to using your little circuits with simply resistors, right? We did add some coils in the motor project, but you didn't really notice what's going on because it actually happens kind of fast. But if one of the things I had you do was at least to check the current flow, you notice it peaked out and kind of came back. Okay, well that was really more to do with the motor, but it has windings in the motor, and it actually sees that as its current starts to flow as an open. It just goes round in circles to a ground. And it's like, hey, let's go. It's a little different than we're talking here. Yes, there are coils. Yes, there's going to be some counter EMF as it starts to build up, but just not enough because of the size of the wire and everything. But what happens is the motor starts to turn, and that creates counter EMF in the motor because of the turning of the armature, and that's similar to what we're talking about. Same concept. We'll get to that in motors. So in a DC circuit, with inductance, meaning coils, with inductance, current no longer changes instantly. The same could be said. I could actually change this DC and I could write AC. In an AC circuit with only resistance, it happens instantaneously. Yeah, it does. It's going to change, and it's going to the amps is going to follow the current. They're going to be lockstep. They're going to go fine. In an AC circuit with inductance, the current no longer changes instantly with the voltage. It's going to be very different. But I'm just having you look right now. Just think about turning on a DC circuit with the resistance. Boom! Instantaneously, it goes all the way through the circuit. You're done. But add in a coil. It's got inductance. Turn it on. It's going to build up slower. So if we could watch the time, we'd see that. So let me see. When the switch is closed, current begins to flow, but is opposed by CEMF in the coil, so it takes time to reach the maximum flow. So when the switch is closed, current begins to flow, but is opposed by the counter EMF that's built up in the coil. At the coil. So it takes time. So it takes time. Takes time for this current to reach maximum flow. The greater the inductance, the more henries, the longer it takes.
When you say the greater the inductance, is that just the more coil?
More henries.
More henries than...
However, we got the henries.
Okay.
And coils are marked in henries, just like resistors marked in ohms. You just can't really measure it with what we have. So it'll be marked. 1 Henry, 5 Henries, half a Henry. You just see that right on there. And that's going to be dependent, again, on the core, what the material is, the shape of the material, if it's long, is it short, is it magnetic, is it an insulator, is it air. You have big wires, small wires, all of that will play effect how many Henries it has. So the opposite here is true. So when the switch is opened, comma, and current tries to drop well to zero instantly. It's not going to. The coil opposes this. It opposes the change because coils are just cranky old men. They do not like change. And it takes time to drop to zero. Takes time.
Yes.
So, kind of like in a basic sense, would you say it's kind of like a capacitor where it stores a little bit of energy?
I'm so glad you said that. And for right this minute, I would say kind of like that.
Kinda.
But in a little bit, tomorrow we're talking about capacitors. You can see it's completely not that way.
Okay. Got it.
If you're like, whoa, but kind of, yes, but not totally, yes.
Is there a way to calculate how much time it will take based on how much henries you have and how many amps?
Stopwatch.
I was going to give her the $1 that I owe for leading me into my next subject. Should have a stack of them right here, or at least pennies. She wants to know how much time it takes. Is this correct?
Yes.
I'm glad you asked. The amount of time it takes for the current to reach maximum is based on time constants. Now, I'm going to tell you right now, this is something, I shouldn't tell you this. A lot of people struggle with this, but it's such a simple little concept. The amount of time it takes for the current to reach maximum, assuming you turned it on and you're going to maximum. Same is true for going back to zero. To reach maximum is based on time constants. So, all right, what is a time constant? One time constant. Is the time it takes, is the time it takes for current to increase or decrease, if you're going up or you're going down, 63.2% of the previous value. Okay, if your brain hurts
It's bad.
and you can barely hang on right here, this is what you need to know. It takes 5 time constants.
Okay.
To equal full value, VALU value, or 0. So in other words, if the circuit is completely off and I close the switch and it's a DC, how long does it take for the current to build to maximum through a coil? How many time constants? 5. Okay, so it's running at full value, and I open the switch. How many time constants does it take to go away? 5. You're done. You put your head down on your desk, take a little nap. Who wants to know why it's 5?
I do.
Done with that?
We all do.
Is it Q&A?
I'll tell you later.
Why does it take 5 time constants? Because why 5? Because, and we're going to do it going backwards because it really only works going backwards mathematically, and then you see it coming back the other way. So if it's already full, it's operating, what percent is it?
100.
It's 100%. It's 100%. And it's going to decrease by how much? 63.2%. So if I do 100 and I subtract 63.2% of that, what do I have left?
36.8.
How much?
36.8.
Thank you. 36.8 is how much I have left. So if I have 36.8 and I subtract 63.2% of that, how much do I have left?
Negative.
No.
What's 63.2% of 36.8?
You have to subtract 23.25.
That number is actually 23.25 right here. 23.25. You guys understand that? 36.8 times 63.2% is actually 23.25. That's the number. So how much do I have left?
13.55.
13.55. So if I have 13.55 left and I subtract 63.2%, which numerically is how much?
8.56.
8.56. So 13.55 minus 8.56 equals
4.99.
I have 4.98 in my notes, good, close enough. So 4.98 minus 63.2%, which is a numerical value of
3.15.
3.15, I hope you're right, equals about 1.83. If I have 1.83 left and I subtract 63.2%, which is a numerical value of,
Oh, I'm counting on you. 1.15.
1.15, I now have a measly 0.67 left, which is 1, 2, 3, 4, 5 time constants. This is considered close enough to 0 that that is the convention. There you go. That's why it takes 5 time constants. A time constant is 63.2% of the previous value. I don't know why they came up with that. Yeah.
63.2, is that a standard 23.25? Is that, where'd you get the 23.25?
Oh, it's 63.8 times 63.2%.
Now where'd you?
Uh-oh, I screwed. Let me just,
Uh-oh.
hang on, we're just going to make it bigger. The numerical value here is 63.2. That's the actual number. So it's 100 minus 63.2 equals 36.8.
Okay.
This right here is a numerical value of, I forget.
No. Is it 43.25?
That's it, 23.25. That's the numerical. So it's 36.8 minus 23.25 equals 13.55.
Okay, got it. Thank you.
All right. So there, it's 5 time constants. Okay, for those of you who want to rejoin us, you can lift your head off the desk. How many time constants does it take?
5.
You're good. And now you know why.
I'm still on DC.
The time constant, because I still didn't tell you how long a time constant is, did I? No, it's like, well, is that a second? Is it a minute? I don't know. Time constant is proportional to inductance, which is measured in henries, but treated like ohms,
Got it right?
and inversely proportional to resistance. So in other words, more inductance equals longer time. How many time constants? But they're just longer time constants, okay? More resistance equals, we'll go less, I said shorter, but we'll go less time. Less time. And the formula is, because it's an easy formula, I'll put it, the time constant Tc equals inductance divided by resistance. So, all right. I didn't cross this out for some reason, so I feel like it must have been important. So, example.
What was it? TC? What is
Time
it?
constant.
Oh, time. Okay.
Example. I just drew a little circuit that looks like this. What is that?
Coil.
Coil, resistance, And we'll say that, let me see, 10 ohms, and inductance, this has 2 henries. By the way, so on some of my stuff I put a little h. It should be a big H because Henry's his last name. So, example, we have our resistance of 10 ohms and 2 henries. How long is each time constant, and how long does it take for current flow to stop or completely flow? So the time constant, Tc, equals inductance over resistance. So what is my inductance? 2 henries over, what is my 10? Okay, so the time constant equals 0.2 seconds. So it takes 5 time constants, 5 TCs of 0.2 seconds each to fully start and stop. So how long is that? 1 second. So that'd be a total of 1 second. So as henries go up, the time constant will increase or decrease? Will increase. As resistance goes up, we'll put proper English, the time constant will decrease. All right, so all of that to say, hopefully you can see with an inductor, voltage will be instantaneous. I want to write this because it's important. This is my so what. How do I say it, Hannah? That brings me to the...
This
Brings me to...
What?
So what? Hopefully, because that's all I got is hope. Hopefully you can see with an inductor, voltage will let's say be instantaneous You okay over there? You make a lot of noise.
Yeah, I've got another piece of paper.
Okay, good. You got that paper out. But it takes time. It takes time for the current to build up, for the current to build up. Therefore, in an inductive circuit, an inductive circuit is a circuit that has more, technically speaking, I don't want to miss this point, has more of inductance than other things. So, I shouldn't say that. An inductive circuit, by definition, be one that is more inductors than capacitors. If it's a capacitive circuit, it has more capacitance than inductors. So an inductive circuit in an inductive, meaning more coils than capacitors. In an inductive circuit, the voltage leads the current. As we mentioned, mostly me, with Eli, the voltage, E, leads in a coil the current. ELI. Voltage, coil, current. Eli. Remember that? We have Iceman. Yeah, that's the first part of the Iceman. Eli the Iceman. Voltage leads the current. So what I just said We turn on the circuit, voltage, boom, it's off to the races. Starts going through it goes through the coil. It's already done. It's instantaneous. It's got the pressure. Here comes the current. It starts going through the coil. Starts building up this counter EMF, this electromagnetic force. What does that electromagnetic force do? It's building up, and it's building across the coils. So you have electromotive force, you have a magnetic force moving across coils, creates current. That current is directly opposite of the current that is coming in. So it's building up a current that's going that way. And the two kind of collide, if you will, and it doesn't make it happen. But it eventually wins and goes through, and it just takes a while. How long does it take? All right. All right. VI, what is this point? But in a DC circuit, this only happens when?
When it turns on and off.
On and off, okay. But in a DC circuit, this only happens at startup, and shutdown. Not exactly the proper terms for electricity, but there we are. Okay, this I need to abbreviate a little bit because it's a little heavy here. What number am I on?
12.
12. All right, so now we're going to, he's got 12. 5 time constants. You got that. You're going to get 1 right on the test. Good for you. You're doing it. Right.
Just wondering, is this all true, or are they just complicated for job security?
Oh my gosh.
Okay, so now we just learned all about how that works in a DC circuit, kind of mixed with AC, but let's bring it into a purely AC, so inductive AC circuit. I don't want to write all this because I think it's a little heavy, and I can lighten it up a little bit. In an AC circuit, current changes constantly. Therefore, the effects of inductance happen constantly. You want me to write that? Anybody but Tobias. He's just trying to get back at me. So
I'm just trying to get as much of this in my pad as I can.
AC circuit.
I'm not writing anything.
AC circuit. See, current changes. Current changes constantly. Right? Therefore, that's what that word is. Therefore, the effects of inductance happen constantly. Let's see. We know counter EMF happens with when the greatest change occurs. I'd rather you got this concept, just kind of saw it. So I did this right here. And I said the greatest, we talked about this a bit ago, the greatest counter EMF happens with the greatest change. So this was 0, 90, 180, 360, right? So my greatest change really happens between here and here, between here and right through there. So if we know that the greatest change happens through here, I could say the same thing happens through here. So whenever we're going through 0, really, is when the greatest change happens. And by change, I mean in a period of time. It goes from way up here to way down here in a very short period of time. Then from down here to up here in a very short period of time. When it gets to the top, just kind of peaks out and then falls suddenly, all right? So, sorry, we have that. So the greatest change happens through there. And we talked about Lenz's law, which really had to do with the amount of change that happens. Say CMF follows Lenz's law and opposes current. Sorry, so I'm trying to make this light.
There's nothing light about this.
Yeah, it's actually not so bad. It's actually, You'll see. It starts that way, and then all of a sudden it just kind of, it's what I love about this week. It just kind of sort of comes together. Most of the class just goes, oh crap, I get it now. We just have to put it all together, okay? We're going to talk about inductors, and we're going to talk about capacitors, then we're going to put it all together, and it's going to be like, that's so simple. You'll be teaching it next week. All right. But this point here just isn't that important, but I just wanted to make it. CMF follows Lenz's law and opposes current change 90 degrees later. We also know that counter EMF is 180 degrees out of phase. Applied voltage said that. But we'll leave this one. Therefore, in a purely inductive circuit, meaning just coils, in a purely inductive circuit. Yeah, it is. I skipped a bunch. So B, purely inductive circuit, current lags voltage by 90 degrees. I'm just going to leave it at that. And CMF is 100 degrees out of phase with applied voltage. But let's just not do that, because let's just go with this. In a purely inductive circuit, current lags voltage by 90 degrees. It's going to be 90 degrees out of phase. So if that black line right there represents the voltage, then the current is going to be 90 degrees out of phase. So here's my 90 degree point. It's going to start right there, and it is going to build up and be 90 degrees out. And this is harder than you think. 0 right here, and then so it's 90 degrees out. Yeah.
Oh, that was my question.
Oh. What? Okay, ready for something easy?
Yes.
Okay. No. Is it a movie? Got a movie? 13? 13. Computing inductance in an AC circuit. It is L total is equal to L1 plus L2 plus L3 on and on and on, which is to say exactly the same way resistors are calculated.
In series.
That is true.
This would be in a series circuit. CALCUL calculated. All right. What if they're in parallel? Well, then it'd be L total is equal to 1 over L1 plus 1 over L2 plus 1 over L3, all of that over the 1, which is the same as resistors. So figuring out the henries of coils is exactly like resistors. Exactly. With one exception. Just so you know. And this is assuming the inductors are placed far enough away from each other
What's considered placed far enough?
That's an engineer to figure out, electrical engineer. I don't have that formula. Far enough away from each other to not create mutual induction. Far away from each other to not create mutual induction.
Mutual or neutral?
Mutual.
Oh, that's like
Mutual, meaning the two don't affect each other. So you have all of these lines that are affecting all of the lines inside this coil, but then those are going to spread out from the coil. Now if you put another coil next to that coil, then you have all the effect of this coil at itself, plus the effects from the coil next to it is going to change everything. So you got to put them far enough apart.
Is there a way, like, are there different formulas to calculate inductance if you wanted them really close together?
Well, I'm sure there are, but I don't have them. Look, we don't even have time to go into parallel. We're just doing series AC, which is, all right. You guys got that? That wasn't easy, hard, was it? No, everybody got that point. That wasn't easy. Okay, back to this. All right, we're at number 14 now.
Yes.
14. All right, inductive reactance.
Oh, they are there.
All of them. Inductive reactance. Inductive reactance is the effect of inductance on a circuit. So we're going to measure it in henries, but it isn't like EIRH, right? We don't get into that. I think there's plenty of time here. So, but it's going to have an effect on the circuit, and the effect is going to be similar to ohms, similar to resistance, but it's not quite, but it's like it. So inductive reactance. Inductive reactance is the effect of inductance in a circuit. One, it is measured in ohms. Crazy. But due to phase shift, remember what phase shift is? That is where the volts and the volts and the amps are kind of not equal. Even if they are equal, it still doesn't count. But due to phase shift is not considered resistance. So you don't have this EIR and then you add it to the R. You just don't. Total. E total, I total, R total. This does not go into R total. It is represented as X of L. That is inductive reactance. X of L. And that's really where we're headed with this. We just got to learn about X of L. Once we get X of L down, boom, we're done. So almost there. Inductive reactance. You guys all right?
No.
But it's so simple.
After 30 years.
How friggin' old do you think I am?
I'm gonna teach us.
I've only been teaching here for a couple weeks now. Inductive reactance is proportional to the inductance, and the frequency. Really, I'm telling you, if you're kind of keeping up, and I mean just kind of, and you're like, all right, I've sort of got that, but I'm like not really, don't ask me about it in 5 minutes from now, you're doing fine. We're going to... Huh? Yeah, okay. Julian, you're always going to be fine. I don't know, man. Somehow you always make it, so don't worry about it. All right. We're going to put it all together. It's going to be okay. Inductive reactance is proportional to the inductance and frequency. In other words,
Furthermore,
if inductance, you really want my in other words because that makes it in simple terms. If inductance, DCTA, or frequency is increased, inductive reactance increases. All right, why do we care about any of this? Well, you don't, but let me tell you why you should. So, it's funny, talking to my father-in-law, he used to work for SMUD about stuff like this. And, hey, guess what I learned, Don? And my father-in-law, he's a cool guy. And so, I'm talking about inductive reactance. And, of course, he gets kind of excited because nobody's talked about this stuff in a long time. He's like, yeah, you're right. We do have inductive reactance. So you think about your house, right, this time of year, right now. What do we have going on? We've got the air conditioner running. That is a motor that is going to pump Freon. The motor has coils. We've got a fan going on top of the condenser. It's a fan and motor. It's got coils. We've got, ballast up here, transformers up here, which are more, right? These? Yeah, more coils going. Everything is coils everywhere. So what is that doing to the current and the voltage coming out from SMUD? It's getting more and more and more out of phase. All right, same thing if I had an airplane, and I'm thinking, well, you know what? It's all set up, but I'd like to add a motor over here, maybe a fan for the toilet, another fan for the pilot, and then we're gonna have a motor over here that's gonna run the air conditioner for ice, and motor and motor and motor. What are you doing to the circuit? It's going more and more and more out of phase. It's becoming more and more inefficient. So what we're going to find out is that's what coils do. They're going to start dragging it all this way. But guess what capacitors are going to do? They're going to drag it back this way. So he's telling me over at SMUD, we got this huge room full of capacitors. And they watch this and starts getting out of phase. Yo, Tony, throw in another capacitor. Boom, there's a capacitor. Brings it back in. So that's kind of where all this goes. But so it's kind of cool. Let me see. Oh man, I've only got like 3 points left. I'm totally done with this. We can move on. So the formula.
You can stay late.
The formula is x of L equals 2 pi f L. This is not something I should rush through, but it's very, very simple. X of L, which is inductive reactance, which is like the resistance we get from coils. It's not resistance, but it's just like it. We even call it in ohms, is 2 times pi, which pi but times the frequency times the henries. Which is what I said. What are the two variables? Their frequency and the henries, right there on the end, the F and the L. Frequency. Frequency goes up. What happens? The inductive reactance go up. More henries go up. It goes up. That's all it's saying. That's not hard. All right. It's time for you to go. We'll pick this up tomorrow. For those of you who, trust me, you're going to be fine.